Tamam. Karşı kameraya mı odaklanmıştım? Hello, everyone. Thank you so much for joining today's webinar session. We sincerely apologize for the IT delay, but we figured out how to fix it. So thanks a lot for your patience. So I'm just gonna directly start our introduction, and then we will go on with our program. So first of all, I would like to introduce myself. My name is Bushra. I work as an international sales specialist at Inovenso Technology, and today I'm going to be moderating this webinar, and I will indeed give you details about the presenters and, of course, our topics. So first of all, before we begin our program, I would like to thank actually our partners, Metrogenics, Materik, and of course, my beloved company, Innovenso, for their efforts and, of course, presentations. So I would like to just, give you some details about our program. So main topic of today's webinar session is actually about the Nanofiber Advanced Filtration Media. So I would like to introduce today's presenters and, of course, companies. So our first presentation will be by Ömer Sahto from Inovenso Technology. The topic will be about pollution preventing biodegradable nanofiber filtration media as an alternative to PPE. And then after my colleague Ömer's presentation, Dr. Sherif Soliman and Dr. Kevin Guo from Metrogenics will give us a presentation about Electrospun nanofibers, performance, problems, and potentials in the air filtration industry, including face masks, HVAC, and respirators, of course, and others. Last but not least, we have the last presenter company, which is Materik. Their topic is additives and novel composites in non-electrospun fibers. So they will be discussing challenges and opportunities, and it will be presented by Dr. Stefan Farias and Mike Pilota. So actually, we will have approximately 5 to 10 minutes of question and answering sessions after each presentation. Kindly take your, notes of the questions that you would like to ask for each presenter, and we will definitely answer them at the end of each presentation. So right now, I will start with a short presentation about Inovenso Technology as the organizer of this webinar, and then we can start our program. So first, as Innovenso, I would like to, give you details about our services and our products. So actually, as Innovenso Technology, we have started our activities back in 2005. And then we actually established as Innovenso in 2010. And we've been in this sector approximately 12 years. And we are, giving solutions for nanofiber research. And of course, this electrospinning technology is definitely our scope of work. So essentially, we have three modes of services that giving us to the customers. We are producing electrospinning machines from lab scale to industrial scale production, and we are offering R&D services for our customers. It can start from feasibility studies, it can be for product development, and of course other R&D services that may be needed for our customers. And then lastly, we are offering contract manufacturing. We are actually developing materials for you, and you may obtain it every month or specific period of time according to your needs. You can have this also service from our side. Yes, we are going to go to the next slide. Sorry, there's going to be a delay, but we are just trying to fix it right now. First of all, if we talk about electrospinning and electrospraying machines, as I have previously mentioned, we are offering from lab scale to the industrial scale. And of course, our machines are incorporates hybrid electrospinning technology. This is a needle-based system. It's the combination of course, needleless and needle-based technology. It's specially designed cornicle-shaped nozzle is available, and it is patented by Inovenso. And of course, we have newly launched a new technology called open surface electrospinning. So as you can see from the background, this is our stream spinner 1000 machine. So this is also open surface system. So as you may see from the background, we have thin slots with an activating feeding system. So this allows users to have continuous jet production. And of course, some specific polymers, you may have more than 5 or 12 or 15 times higher production rates. Of course, it's depending on the polymer and the parameters. But if you would like to learn more about both systems and both technologies, you can contact us at sales@inovenso.com address, so we can give you more information and details about your production needs or any other R&D services if needed. So next slide, please. So this is an example image. As you can see, this is a hybrid electrospinning system. You can see there's a rod and there are multiple nozzles, and this is a cornicle-shaped nozzles allowing you to have multiple jets. And this is, of course, giving more production rate for the needle-based units. We can come to the second slide, please. So for industrial scale production, as I have mentioned previously, you will have two options available for you: hybrid nozzle system, needle-based, or if you prefer open surface system. But we have also another good news for you. If you would like to obtain both systems, we offer interchangeable option. So you can have, hybrid system plus open surface system. So you will be definitely having both technologies in hand if needed. And all of our devices are very easy to use. They're all plug and play systems, and it can run for the long shifts. So this is a hybrid electrospinning visual. There are, of course, rods and multiple nozzles integrated. So we can come to other slide. This is the open surface electrospinning. As I said previously, there are, of course, thin slots, and you can see that there is no needle here. So it is, of course, open surface. So we would like to show you the difference between open surface and hybrid electrospinning in a very short video. I would be happy to show you how those machines work. So you see, here is the visual and the video of both systems. This is a close-up.
You can see the main differences between them. One is being lashed on the surface, and the other one is being fed through the needle. So yeah. One has an active feeding system, as my colleague Bushra mentioned. It's moving, and it has a specific needle that emits or deposits solution onto the surface of the highly conductive spinneret. And that allows the emission of jets. Whereas in the right side system, you have a rod of continuous hybrid nozzles that are being fed or pushed through with a peristaltic pump and causing the jets to emit in a multi-needle form.
Thank you so much, Omar.
So we can move on to this.
So as I mentioned previously about our R&D services, our services are composed of course, a lot of let's say, opportunities that is available for you. So we have a literature review, we have feasibility studies, we have early trials and optimizations. And of course, this optimizations allow us to scale up to multi-nozzle system. And then later on, it can be, scaled up to the industrial production as well. So of course, industrialization is possible. So if you would like to have an R&D research, we can have a literature review, feasibility study, and we can have this actually R&D service to be scaled up to the industrial scale production. It can be, possible to obtain. So we can move on to the next slide, please. So for the contract manufacturing, if you have the ready recipe and you would like us to actually handle all the production, and of course, if you would like to order this product in a monthly basis or yearly basis, that's completely possible. So we can use our pilot and industrial scale machines for you. So if you would like to have the hybrid machine, or if you would like to, require open surface, it's completely up to you. We can handle all the, manufacturing part. So how much you would like to, receive depending on the materials feasibility, of course, and how many linear meters of feed that you requested. This is definitely up to you, but we can give you more details if you can reach out to us. So thanks a lot for your time and patience. You can contact us and at the same email address, sales@inovenso.com, so we can give you more details about our products and services. So thank you so much for listening this short company presentation. So right now we can move on to our program. And first I would like to actually maybe introduce my colleague right now. Thank you, Ömer.
Thank you, Bushra. Allow me to formally introduce myself. My name is Ömer. I am the R&D support engineer at Innovenso for the R&D team, and I will be talking about, I'll be giving a presentation about biodegradable filters with Electrospun media. So let's see if we can get the file up and running. Right. So yeah, so pollution preventing biodegradable nanofibers. So I'm going to talk about the electrospinning process of these biopolymers and see their applications too. So we can move on to the second slide. So yeah, I'm just going to give a small like a rudimentary definition checklist, so that before beginning, I could just define these things. So nanofibers are one-dimensional nanomaterials which have diameters in the nanometer range, or rather at least in the submicron range. And electrospinning is the electrohydrodynamic process that helps you enables you to create a mesh of these, which you can then see from an SEM. So let's move on to the next page. Right. So as we all know, nanofibers actually, in terms of application, the most well-known and the most remarkable application would be its capabilities for filtration, specifically air filtration media. This is because of its advanced features, advanced properties rather. It has such small fiber diameter, and it helps basically to have mechanical capture of the PMs, particulate matter, whereas in the conventional filters you would normally have them electrostatically charged. Another interesting thing is that it may enable you to have lower pressure drop. That's because having smaller fibers and given the proper thickness, it would incorporate a slip flow regime. So what that means is when it passes, when air is passing through the filter and the particles are being bombarded through the fiber, it doesn't lose that much momentum as compared to when they're hitting the microfibers, and so that results in overall lower pressure drop. And they're also having high surface area over or volume, which allows it to have maximum efficiency, and also enables it to have some lightweight features. So it can be considered to be the next gen for filtration media, and it is actually picking up speed for such an application. So we can move on to the next slide. So right, so we talked about it's being used for filtration and air filter and usage disposal. So nowadays, especially in specific polluting environments and with environmental issues, these filters, specifically mass media and also HVAC filters, they're being used more and more, and they need to be replaced after every 3 months, or especially air purifiers, which you might need to change every month. So depending on what filter you're using. Also, due to the advent of due to the recent pandemic issues, that even face masks have been exponentially increased in their usage. All of these specific filters and mask media, they're actually thrown out and disposed of after being used. So this is all fine and dandy, like all of these applications, but what we need to determine is its recyclability. So we've had past clients come to us, approach us about this, about having like, so you see an increased usage, so you also have an increased rate of disposal, which actually adds to the pollution. And then the factor of recyclability comes in. So we can move on to the next slide and talk about if they can be recycled or not. So moving on. Right. So actually, it turns out you really can't. The standard filters that you're using, and even that includes masks and HVAC, you can't necessarily just recycle them. They're once contaminated, they're actually sent to a landfill, and this basically accumulates in pollution. So they can't be easily recycled, and because of the recent pandemic issues, not just masks. Of course, masks have been increased a lot, their usage, the frequency of usage, but also the filters too, because of commercial buildings or certain residential buildings trying to keep clean air in. So there have been a lot of discard cases, and we have basically an environmental issue at this point. It has an impact on it. So let's move on to the next slide. Right. So coming back to masks, so you have an issue with so you're having an increased usage of masks, and eventually they need to be thrown out, and they're not specifically they're not, as I mentioned, biodegradable. This leads to continual waste, and so this is actually a problem, especially in this due to recent times. And so what the issue comes about is that you can't necessarily stop people from minimizing the use of masks, especially for their own safety. So there would have to be a way, and this is what certain clients came to us and asked a request of service for, is that how can we continue using masks or using filters without having a detrimental impact on the environment. So what could be the solution? So this is where biodegradable mask comes in. So we can move on to next slide. So we talked before that nanofiber media can be used as filters, and certain polymers are electrospun into nanofiber meshes. So if certain biopolymers themselves are also biodegradable, then practically speaking, if you were to electrospin them, theoretically rather, you would have filters that in nanofiber form that can act as filters and masks while also being biodegradable, because the polymer themselves that they're based off of is biodegradable. So we have certain potential candidates, and not just potential, I think suitable candidate is the better word, because there's proof of this. So that would be PLA, PHP, PCl, and PVA. There are other polymers as well, but these are the ones that we have specific experience in, and we're going to talk about them in the next slide. Okay, so before I continue, actually, I rather there's actually a specific issue with. I mean, there seems to be sometimes rather a confusion about like the definitions between these three terms: bio-based, biodegradable, and compostable. So before going further, I'm just gonna differentiate them so that we're all clear in the matter. Bio-based does not mean that it's biodegradable. If a polymer is bio-based and electrospinnable, doesn't mean it's going to degrade. It just means that it's derived from biological organisms, not that much chemically hazard, but it doesn't degrade. It will accumulate in landfill. Biodegradable is actually, the second term is actually what we're looking for, what we're targeting. It's basically material that can decompose over time, and due to the presence of living organisms, so bacteria eats it away. And compostable is not biodegradable. It's specifically a material that can be decomposed or certain compostable conditions or certain cases. So we're focused mainly on biodegradable. So let's move on to the next slide. Right. So I'm going to talk about how our R&D process works and how we're um, specifically how we approach the situation and how we come up with a solution. So we start, of course, at the lab scale prototyping. So if you have like the biological polymers I mentioned before, and if they're electrospinnable, so we can produce a mesh of nanofibers and then test them out and see if their filtration efficiency or pressure drop is good. So the first task I would like, actually the first challenge I would have to say is biodegradable polymers tend to have an issue initiating their Taylor code. At least 3 out of the 4, we had issues with that. The aforementioned polymers. Actually, that could be attributed to their complex nature, the structures. So they tend to have a strange emission jet formation, and actually you can't really control their jet that well, and also because of that, clogging issues may arise. That's one challenge that you're going to face if you're looking for electrospinning biodegradable media. Another issue is the solution preparation. So there are certain cases that you can use a solvent and dissolve that polymer, but you may not necessarily be able to upscale it. They might be too dangerous. Something like certain cases, you need to worry about the solvent that you're using, and because when you switch over to when you transition to the industrial scale, another issue you might face is that the solvent of course, when you're transitioning, you're going to use a large amount of more solution, like quantifiably more, and it's dangerous if your solvent is basically maybe volatile, or especially in the case of if it has a very low flash point. So we wouldn't recommend you using like polymers that have very low flash points, especially in industrial scale, because there's chances of fire hazards. So that's one issue. Another issue is that if it's a bio-based and degradable polymer, solution aging could also affect the process. So if you're going to set up a mass manufacturing site, you might need to consider like how you're going to go about producing the solution and electrospinning it as possible, because if you were to store the solution, there might the morphology of the nanofibers might differ or might actually worsen because of its degradable nature. So yeah, production rate may decrease and inconsistent, of course. So this is something that you need to do at the lab scale before you worry about the industrial scale, and so that you don't have these issues coming about in the industrial scale, which I'll talk about next slide. So let's talk about scaling up. Okay, so this is where actually the real fun begins, because then we have to talk about a lot of parameters and a lot of things you need to consider when you're trying to optimize it for commercial scale filters. So you need So when you have a prototype at lab scale, it might work well for the lab scale. It might work for one single needle perfectly fine. But when you use multiple nozzles, or if you even switch over to the open surface system, you're gonna get you're gonna find that it's not necessarily like you can't just copy paste the recipe, or rather the operational parameters. You would need to adjust them, of course. So there's going to be larger flow rates, of course. That's the first point, and leading to faster production. So you need to attune the voltage, or specifically maybe even the speed of your roll-to-roll system, so that it doesn't so that there's no mismatch, or there's no low deterioration during the production. So that's one thing you're going to have to look at. The other thing I want to talk about is, so I talked about the recipe not guaranteeing the same industrial. So the third one is actually also, I would say, just as important. It's something that you really need to consider: compatible substrates. So this is not just this is like, first of all, it's going to have be biodegradable. So if you have an electrospun nanofiber media that's biodegradable and has good filtration efficiency, it won't mean much if it's latched onto a non-biodegradable substrate, especially if you're going to use that layer for converting into a mask or maybe a filter. So yeah, you need to make sure that the substrate that you're using is biodegradable. That's the first important thing. Secondary stuff are also pretty important. You need to worry about its adhesion. So you might be able to set up a pre-coating, or maybe like coat it in adhesives before, but if it has low adhesion, that could be very, very problematic for you later on, especially if the nanofiber layer can just peel off. So the substrate needs to have higher adhesion, or actually relatively good adhesion for your nanofiber layer. So adhesion is one thing. Another important thing is, actually this is very important, like strength. So like let's say cellulose filters, or maybe something derived from cotton, it's biodegradable, but in our past we've noticed that, okay, it's not mechanically strong enough for the roll to roll. So they might, so when you're setting up a large manufacturing, a part of the biodegradable filters, you're going to do roll to roll, as you see in the machine here. If your substrate isn't strong enough, it'll tear off, or even if it doesn't tear off, if it just thins out, you just basically compromise the whole production cycle or the roll. So that's something that you want to avoid. So it has to have mechanical strength for your roll to roll tension. Of course, that depends on what type of how much tensile strength it can withstand, and also the type of roll to roll you're using. And finally, the substrate needs to have an anti-static property. So its static behavior matters. So in the past, if you were to say like some substrates that you're using as like spun bond media, like let's say for example polypropylene, which is really well known, it tends to accumulate charge. If it accumulates charge, it can basically repel the fiber jets. So that's something that you want to avoid. So you could, like for the case of polypropylene, it's not biodegradable, but for that case you could treat it to make it have anti-static properties. But yeah, for your substrate, it needs to be able to be anti-static. Otherwise, if that's the case, if you were to electrospin it, you'll notice some regions where the nanofibers layer membrane wasn't homogeneously distributed. So something that you basically need to think about before continuing onto the industrial scale. Shelf life, storage conditions, of course, the polymer, it will deteriorate over time. So you need to choose, like the polymers that I've mentioned before, it needs to have a longer shelf life so that it doesn't like ruin its quality, or like if it stayed and stored, it doesn't basically deteriorate or rot away. Or compromise its filtration efficiency. Post processes may be needed depending on the polymer. This depends also on your application and the type of filter being used. But yeah, that's something that comes after all that. So let's move on to the next slide. Right. So I mentioned before, to basically to try to have a manufacturing line, you need machines like these, basically the open surface technology. I mentioned before that that these polymers tend to have clogging issues, especially on most gauge diameter nozzles or needles or whatever. But in the open surface, we actually bypass the clogging issue because you're just placing the solution on the surface. And we into our experience, it actually these polymers that we mentioned before, they work much better on the open surface system than they did with the needle-based system. So it's actually amazing. It's not just that the production rate increased really severely, but it actually ensures a continuous process because there's no clogging going on. So of course it needs to be optimized and designated, and you can have a couple of machines similar to these that can help you set up a manufacturing plant in the case you want to commercialize it once you have your ready recipe. So let's move on to the next slide. Okay, so what exactly can be produced? So let's say you have these biodegradable filtration media that have specific fairly well filtration efficiency, good pressure drop. They can be used for mask media. So you have these roll-to-roll collected filters, they can be sent to the mask making machines, or if you need to post process them, deplete them for HVAC filters, that's something you can certainly do for ventilation, for HVAC, for air purifiers, etc. So let's move on to the next slide. Right. So I'm going to talk about our experience thus far. So we have successfully produced a recipe and an optimization method and a production method essentially for a specific client of ours for biodegradable masks for the scale of, I believe, N95. And we were able to do so just by following what we've done before for the normal common polymers like PVDF or nylon, but with, of course, the biodegradable polymers. And we were able to get a manufacturing site for them up and running, and they are currently producing biodegradable face masks. And the second one for HVAC filters, we're actually working with the company right now. We're in the transition phase. We're actually in the in-between phase of from lab scale to industrial scale. We're basically working on it for air filters, for environmentally friendly air filters. So it's a work in progress, but we've been getting good results and we're hopeful. So let's move on to the next slide. So yeah, I'm going to talk about certification. So I'm not going to go too much in detail because it's not our forte, but standards and testing. So when you have the filters, you may need to consider testing them to certify if they're if they meet what the needs are. So EN 143, EN 149 for the European standards, NEOSH for North American standards. They vary. They have some differentiation between them, but the essentially core testing concept is the same. They measure the filtration efficiency with an aerosol or a particle of choice, like could be sodium chloride, could be even a DHS, depending on what the test covers. And for filters, regular like HVAC filters, you have your ISO 16890, you have EN 1822 for even advanced filters like HEPA OPA. And ASHRAE 52.2 for the North American standards. So these are just for this also measure the filtration efficiency and pressure drop, along with other things, depending on their special methodology for testing. So let's move on to the second part of standards and testing. So yeah, you have to come for biodegradable testing. Now there's various forms of these sort of tests for biodegradability, and also depends on what site you're talking about. So the one here is like ASTM D5526. It's actually much longer than the D5511. It's actually they're basically both tests cover they're basically placing the plastic or polymer material in a controlled replicated, you could say, landfill environment. And these are pretty long tests. Even the 5511, it could take up a month or so. And they measure basically they determine the biodegradability under anaerobic conditions. There are also aerobic condition variations of this test. Also, this is covering for soil. There might be also for aquatic zones, and they also cover anaerobic or aerobic. So it depends on what you're looking for, what you're looking to target. And then once you have a ready a product that you have confidence in, you can choose the test that you need accordingly, so based on what you need. So let's go on to the other slide. So yeah, so in summary, I'd like to say that, okay, so it's the same concept. If you electrospin biodegradable polymers and they come out in nanofiber mesh form, you can use them as for filtration media, both for mask and HVAC. They are trickier, of course, to electrospin. There's a proper R&D format, of course, to carry out this, as I mentioned before. And the basically the major advantages is that you have nanofiber grade filters. Okay, so they have high filtration, lower pressure drop if you attune them, and can be post-processed. And of course, they're environmentally friendly, so they don't have a negative impact over the environment, and they will eventually biodegrade over time. So yeah, essentially that covers it. So let's go to the final slide, and I'd like to say, thank you for your time. And if you have any questions, I'm all ears.
So thank you so much, Amer, for this informative and really nice presentation. So right now we are having a question and answering session. So if you have any questions, please type down in the chat section so we can address them. So it will be 5 to 10 minutes according to your questions. And then later on, we're going to move on to the second presenter company. So we're just going to wait for a couple of minutes. So we will wait for your questions. If you don't have any further questions, we can move on for the next presentation. So I'm just going to remind you about the maybe next presentation topic, so you can think about your questions. So I believe Dr. Sharif Soliman and Dr. Kevin Guo from Metrogenics will give us right now a presentation after my colleagues Amar. Oh, sorry, there's one question. Let's read it. What are the biodegradable substrates you have used to
Used for, yeah, I
yeah,
see.
for the
Used for the
company.
company. Thanks for the great,
Thank you.
thank you so much. I appreciate it. Unfortunately, we're due to confidential reasons, we can't really reveal what type of polymers we're using. But most likely the polymers that I mentioned before, you can certainly consider them for even a combination of them if you'd like for those filters for biodegradable masks.
So we have another question. So
do you reach to the finally formula for the filtration media? So yeah, so I talked about mask media. We have air filtration mask media and we have it ready, good to go. For the HVAC filters, we're still working on it, but we're coming pretty close. Like we basically have a really good lab prototype, and we're trying to find a way to have an optimized upscale production of that. So yeah, it's a work in progress, but we're hopeful.
by the way, if you would like to ask your questions, we can unmute you and you can, have the microphone. Mm-hmm. And if you would like, you can ask us verbally. So we have another question. Can we make it a little bit bigger, please?
Yeah, so you
Thank
can see.
you.
Mm-hmm.
We're just gonna answer it in a minute. Okay.
So what the problems and challenges you faced when you try PHP? PHP is such a great biodegradable polymer material. Have you developed a formula? Mm-hmm. So PHP, we have some working formulas, and it does. You're right. It's a really good biodegradable material, I would say. It's so a couple of challenges. It's very conductive. And you might need to, I would say that you might need to consider it's when you're trying to electrospin it, you might want to take a keynote on the flow rate, especially when it's when you're trying to make sure all the Taylor points are emitting. So yeah, essentially that's the case. Other than that, you can basically try other like material polymers for that. So let's see the other question. Can you please elaborate a little bit for more on post-process you have mentioned? Right. So let's say you have your workable material ready. You may want to basically pleat it if it's an HVAC filter, or if you're using or shape it rather. And for mask the same, you might want to shape that also for the mask. However, certain post-process may be done for, like, let's say for the example of PVA I gave. PVA is actually water soluble, so you might want to have certain post-process to make sure to decrease its solubility, let's say like that. After you electrospin it, you may want to try cross-linking, or you may want to try to make it less soluble as possible, because it needs to be in ideal conditions for that. So yeah.
So I believe we have those questions.
Mm-hmm.
Okay.
So let's see if there's any.
So if you have any further questions, you can send us via email, and our emailing address is sales@inovenso.com for all sales and marketing questions that you may have. We would be happy to give you more details about our machinery and products and services. Please reach out to us via email. So let's move on to our next presentation. So I would like to present Dr. Sherif Soliman and Dr. Kevin Guo from Metrogenics. They will give us a presentation about Electrospun nanofibers, performance, problems, and potentials in the air filtration industry, including face masks and respirators, HVAC, and others. Let's welcome them and let's hear what they're going to tell us. Dr. Sherif, I believe your microphone. Okay.
Kevin, can you actually unmute Kevin, please?
So Dr. Sherif, you would want us to unmute Mr. Kevin?
Yes, please.
Okay, can we please unmute Dr. Kevin? Okay, we're just handling it right now.
Hey, Aaron. Thank you.
Thank you so much for your time, sirs. We would be happy to listen to your presentation, and we are eager to learn what you are going to tell us today.
Pleasure's on us. Do you mind let me share my screen?
Of course, indeed, you
Absolutely.
can. Okay, I think you can share, Dr. Kevin, your screen. Can you please try? Thank you.
Can you guys see my screen right now?
Yes.
Yep.
Okay. So, good morning and good evening, everyone. And my name is Kevin Guo. I'm the CEO of Metrogenics. I will present this topic today. Our CEO, Strafe Solomon, he's here with us, and he will assist me for the Q&A session. So it would be great if you guys can unmute him as well. Metrogenics has been focused on developing nanofiber solution for air filtration in the past couple of years. So today we are going to share our experience and thoughts on these topics. Before I start, I would like to give a brief introduction of who we are, what we do. Metrogenics is a nanofiber technology startup. We utilize nanofiber as a platform incorporated with our strong IP portfolio and the team to develop different nanofiber products. And right now we are focusing the biomedical and the filtration sectors. And with our technology, Metrogenics is able to bridge the gap between the nanofiber product development and the commercialization by tackling the difficult problem in this area. For example, we are able to establish formulations and the electrospinning standard operating procedures to elevate this long R&D commitment and also reduce the batch-to-batch inconsistency. By using the Innovenso state-of-the-art pioneer electrospinning machine, we're also able to scale up our process and significantly boost our throughput of our production. Today's talk it's construct and to walk you through from these three major areas of nanofiber in air filtration. We will state some facts and also share our own thoughts and experience in those three areas. In second section, we will do some showcasing for the some application of HVAC and face masks. First, I would like to talk about what's the value of nanofiber filter media in the air filtration industry. In the filtration space, due to the nature of a nanofiber filter media, the nanofiber with the fine fiber diameters is able to construct this complex pore structure, which enable a high filtration efficiency of fine particles with the most penetrating particle size. At the same time, in order to reach same level of filtration efficiency, nanofiber filter media require much less thickness compared with other regular filter media materials such as melt blown. And also, nanofiber filter media able to offer an extremely low pressure drop due to the slip flow effect. If we look at this image, when the air molecule travel through the nanofiber filter media, it has very slow impact of the fiber surface. It's able to allow the molecule maintain their initial flow velocity, thus minimize the airflow resistance. In addition, the nanofiber filter media also tend to have longer filter life and easier to be clean. The way how nanofiber capture the fine particle is rely on this pure mechanical surface trapping mechanism. So the filtration performance doesn't deteriorate with time, not like melt blown, those like static charge filter media. so it can maintain this performance for a long period of time. Since most of the particles accumulate on the surface nanofiber, it's easier to be cleaned by simply applying a backpass pressure. By the nature of the electrospinning process, it's really easy to functionalize nanofiber surface by some active agent, for example, some small molecules and some functional groups in order to achieve certain kind of properties such as antiviral and VOC removal. The last but not least, nanofiber filter media also has great reusability, antibacterial property, and flexibility. Due to all those unique properties for nanofiber, nanofiber filter media has been applied in many air filtration products, including face mask, respirator, HVAC filters, air intake gas turbine, and some functional air filters. So next, I will introduce some of applications in this nanofiber in air filtration. Since Metrogenics has been developing the filter media for face mask and HVAC, I will focus on those two applications. The first showcases the nanofiber for face mask. Due to the pandemic and the drawbacks of the current melt-blown face mask filter media, for example, the melt-blown has this limited shelf life due to the static charge deteriorated with time. It's become a significant concern for the government who wants to stockpile those masks for the future pandemics. In this case, nanofiber provides a much better alternative due to this longer shelf life and the pure mechanical trapping system. At the same time, we also did a hand-by-hand comparison with the melt-blown filter media in different characters. From the data, we can say the nanofiber filter media has great advantages, including higher filtration efficiency, better reusability, lighter weight, and same time, a better breathability. Regarding the breathability, nanofiber media, many studies shows nanofiber media has a better moisture and carbon dioxide transmission properties. If we look at this image, that deep blue and the red area indicate the moisture and the carbon dioxide easily travel through, penetrate the mask made by nanofibers. In US, different mask respirator products is regulated by different standard, and each standard has their own required testing mechanism. For example, for N95, it's regulated by NIOSH, and it required this rigorous testings, including filtration efficiency, pressure drop, aerosol loading test, and fading test. For the surgical mask, most testing is based on the ASTM F2100 standard, including flammability, particle, virus, bacterial filtration efficiency. The filter media we developed for the face masks has passed all the tests listed in this table. And next, I would like to talk about the nanofiber filter media in the HVAC, especially for the HVAC 13, MERV 13. At the beginning, I want to explain what's the current problem in this industry. ASHRAE and CDC has been increasing the regulation for HVAC filters due to the indoor air quality and the pandemic. And recently, ASHRAE just updated their guideline for commercial building HVAC filters. It's increased from MERV 8 to MERV 13. MERV is a filter standard regulated by ASHRAE. A higher number give you higher protection. The problem here is most common current HVAC system is built only fit 2-inch depth filters. And it's extremely difficult to make the MERV 13 filters with only 2-inch depths due to the high airflow resistance. In this case, nanofiber is a great solution for this problem due to the high filtration efficiency and the low pressure drop we mentioned earlier. By simply apply a thin layer nanofiber coating, nanofiber is enable the filters to achieve the MERV 13A filtration performance and without losing the 2-inch depth. And we also collect some data based on our own developed filter media and the benchmark with regular MERV 13 filters. So if you look at those graphs, you can see nanofiber filter media shows over 40% higher filtration efficiency with a similar pressure drop compared with regular MERV 13A filter. However, the nanofiber filter media without dust holding capacity layer does show inferior in terms of dust holding capacity performance, which is not ideal for the HVAC filters. But this problem can be easily addressed by adding another dust holding capacity layer on top of the nanofiber. For example, we can add another melt blown layer. The last, I want to talk about some current challenges of nanofiber in the air filtration industry. The first, for most air filtration product, the filter media has to go through the pleating process. In this case, it requires a strong adhesion between nanofiber layer and the substrate in order to maintain the integrity of the filter layers. So there are some solutions, and we have been investing some of them. The first ones, we can apply a glue layer before the electron spinning process, so in order to increase the adhesion. Second, we also can laminate another protecting layer on top of the nanofiber to maintain the integrity. Third, we also can simultaneously spin another lower melting temperature polymer combine it with the current polymer, and later on apply a heating process so the lower melting polymer become the glue to enhance the adhesion. Another problem is scalability. In this case, there's two major limiting factors. First one is equipment. If we look at this first picture, this old ugly benchtop equipment definitely not going to help us with the scalability problems. By the way, this electrospinning equipment is built by our CEO, Shrif Solomon, many years ago. Here, I wouldn't tell which year because I don't want to reveal his age. Let's just say it's old. Luckily, right now, Innovenso is able to produce this state-of-the-art industrial scale electronic spinning machine. Is significantly enhance the throughput of production and help us to solve the scalability issues. The second limiting factor is the reproducibility for nanofiber products. Due to a large number of variables of electronic process, it's really difficult to control the consistency of the nanofiber product. Based on our own experience, over 90% of those inconsistency of the product coming from the solution preparation steps. In that case, we have implement rigorous material inspection and SOPs to help us to address these issues. To conclude, the nanofiber filter media has a really strong value proposition for the air filtration industry, and the nanofiber is able to offer better alternative for face masks than melt blown material, and also can be applied to HVAC filters in combination with a capacity layer. And currently, there are many solutions, and the potential solutions will expedite nanofiber adoption in the air filtration market. Thank you for listening. We would be glad to take any questions. If we are not able to answer all your questions, please feel free to contact us. We would love to answer all your questions and inquiries offline. Thank you.
Okay, so thank you so much, Dr. Kevin, this informative meeting. If you have any questions to Dr. Kevin and Dr. Sharif, please do not hesitate to, type down in the chat section, or if you would like to, have the microphone so we can give you a word so you can ask your own questions to them. So we can wait for a minute. So if there's any question, you can, ask Dr. Kevin. So as Dr. Kevin mentioned, if you have any further questions about his presentation and his topic or their applications, please contact Metrogenics, and their email address is info@metrogenics.com. So you can definitely contact them for further questions or any other information that you request from their side. So I believe, is there any further questions? Let's check. If not, we can maybe move on to the next presentation, if you allow me.
So, okay. So there doesn't appear to be any questions. However, if you want more info, please do make sure to visit the Metrogenics website to get more idea about the company. So
thank you so much, Dr. Sharif and Dr. Kevin, for the presentation again. So we can move on to the next presentation. So we have a last presenter company, which is Materik. So their topic is additives and novel composites in Electrospun fibers, discussing challenges and opportunities, and it will be presented by Dr. Stefan Farias and Mike Pelota. Let's welcome them and let's listen how they're gonna give us more details about that topic. So thank you so much, sirs, for this pleasant meeting and of course the presentation. Let's move on.
Yep, thank you so much for introducing us. I'm Stephen Farias. My PhD is in material science and engineering, and I'm the co-founder and CSO of Materik. And I'm here with our production manager, Mike Pelota, who I'll let introduce himself as well.
Hi, everyone. Mike Pelota. My degree is in chemical engineering with a concentration in materials, and I'm the production manager here at Materik.
Great. So just a quick overview on Materik. We're an advanced materials and manufacturing company, and we have a number of capabilities across a number of different advanced materials platforms, including electrospinning and nanomaterials. And so that means we have specialty inks, some different biomaterials and printing processes, as well as specialty textiles that we can bring around our electrospinning capabilities to really provide a unique offering to our different clients. And in terms of electrospinning capabilities, we have multiple units. We have a lab unit just like Metrogenics just showed, but I don't put those on pictures because they don't look pretty. But we also have a couple commercial units, including roll-to-roll needleless, needle, nozzle, and coaxial spinning units, some of those through Inovenso, and others through other companies as well. And that really gives us a great suite of capabilities to do different fabrication processes as needed for our clients. We also have post-processing and characterization. And by being part of a larger group of advanced materials capabilities, we can bring a lot of different capabilities to the electrospun materials that we work on. So I'll let Mike go ahead and describe some of the images on the right.
Sure. So on that top left image, you'll see what Steve was describing as a roll-to-roll needleless system. So that differs from, I think, a conventional lab electrospinning setup in that there's no needle in which the polymer solution is being forced through and then the electric field is being applied to. This allows for a high throughput of Taylor cones as you're depositing solution onto a wire, which allows for more solution to be drawn up onto your deposition substrate. Versus to the right of that is the Innovenso PE550, which we have at our facilities, which is a needle and nozzle based system. From there, we can get a little bit more tunability on the nanofiber side. Although they're different in their nanofiber production mechanisms, they both follow the general rules of electrospinning, which is forcing a solution into a Taylor cone by applying an electric field and then capturing the nanofibers produced onto some sort of substrate or deposition section with an opposite charge relative to your charged surface, creating the Taylor cones.
Mm-hmm. And a number of these capabilities are through Materic's subsidiary company, Dipole Materials, which has been electrospinning novel products for some time now. And in terms of who we work with and how we work with, we really are a custom development and manufacturing shop. So we have a couple of our own products, but really we work with clients who have specialty requests in advanced materials and nanofiber production, and really bring our team of experts together to help them solve their advanced materials needs. And when you hire us, we work with you really as part of your engineering team and partners to get you to market. And we do everything from ideas, vetting different concepts, actually going with prototyping all the way to commercial production. And we're going to talk about additives and composites among electrospun materials during our talk today, with some focus on filtration, which is the kind of theme for the webinar. And we work with these materials for a number of different industries, so different air handling and masks, like the Metrogenics speaker just spoke about, but also other filtration applications where composites can be useful, including chemical and industrial environments where we care about VOCs, maybe CO2 capture or potential hazardous vapors in the working environment, and then liquid media as well, where there might be a filtration for industrial oils, electrochemical baths, or other kinds of processes. So nanofibers are used in a lot of different industries, and additives and composites can bring a lot to that in terms of adding additional functionality on top of the sort of fiber size and air permeability and back pressure benefits that you get from working with a nanofiber.
And as Steve was mentioning, sometimes your nanofiber is your filtration media, and sometimes it doubles as carrying for those additives. So in the second case, like chemical and industrial environmental filtration capabilities, the nanofiber acts as both a filter and a carrier for those additives, which can be used for either chemi-absorbing or doing some reaction to the volatiles that are coming off that need to be filtered. And in some cases, between the second and third bullet, the chemical and industrial and the liquid media, you'll find that you could tune your nanofibers and their area density to help filter different types of materials, whether it's a liquid or a gas.
So there's a lot of different options for working with additives and composites in electrospun fibers. You can do polymer blends where you've got multiple polymer types forming during the electrospinning process. You can do chemical additives either in your electrospun solution or as post-processing. And we're going to focus on this talk in things and challenges when you're working with particulate additives. So that's things like carbon structures like graphene, carbon nanotubes. We've worked with metal organic frameworks, ceramic nanoparticles, metal nanoparticles. There's a lot of different options you have to actually incorporate these different additives to add that functionality on top of the nanofiber geometry and porosity that you're going to get from an electrospun material. And then there's also post-processing methods, whether that's a liquid coating. Sometimes you can do thermal treatments of your electrospun material, or even vapor coatings or atomic layer deposition. But the focus of what we'll talk about here is really things that we look out for and things that we try to design for when we're working with solid particulate additives. And so there's different kinds of composite structures you can get out by adding solid particles into your electrospun nanofibers. You can work to try to get a homogeneous dispersion, or you can, or just as an as-spun material, you can sometimes get particles that are purely in the interior of a fiber. These are just schematic drawings of a segment of a fiber, or even on the external surface. And a lot of that will depend on the actual surface energies of your particle related to your polymer that's solidifying as your Taylor cone is drying, as your fiber is drying, as well as their interaction with the solvent. And so if there's some kind of bias where the particles want to be interfaced with the solvent more than the carrier polymer does, then you might have this case where particles are actually speckling the outside of the fiber. Where if the opposite is true, where then the polymer material really wants to be more interfaced with the solvent, then you might get particles that are almost purely in the core of the fiber. Or if it's mixed, you might get some homogeneous dispersion of particles in the fiber. And then in some cases, for instance, with some Innovenso instruments, you have capabilities in coaxial spinning. You could intentionally have a core polymer that has your additive particulates in it, and then be coaxially spinning a shroud polymer around it. And then with all of that, we also care a fair bit about the size of the particles compared to the fiber diameter size. They can influence each other, and if the particle is very, very small compared to the fiber diameter, then maybe you can guarantee it's going to be fully interior. But if it's large compared to your fiber diameter, it's just not geometrically going to fit into that space.
Great. So I'll start to touch on sort of what we've learned empirically through prepping solutions with additives. When prepping a regular polymer solution with just the plastic and your polymer and your solvent, it generally for stock solutions becomes easier in that you can prep the solution either the night before or the same day and then have it spin. And most of the legwork on optimizing comes via the electrospinning conditions. When adding an additive and creating a suspension or an emulsion, the prep for the solution is just as, or in some cases, even more important to make sure that that goes well. I say more important because your spinning could go well, but if your nanoparticles or your additives aren't dispersed correctly or prepped correctly, your final product still might not function the way you had it intended. So we start to combat some of the issues we run into with additives via, I'll explain via these bullets. The first one is deagglomeration. We'll find that nanoparticles, if they're tacky enough, will stick together, and that will end up affecting the uniformity of your final product. So we'll use methods like horn sonification and vortex mixing in order to break up and make a uniform solution such that when we spin, nanoparticles and additives are spread uniformly throughout our final nanofiber mat. We found that the amount of time required to appropriately deagglomerate nanoparticles will vary between horn sonifying and then vortex mixing for 15 minutes total between the two. And sometimes it's on the order of hours, 2 to 3 hours between the horn sonification and the vortex mixing, just to make sure that we can have that uniform solution. When it comes to the mixing conditions and the energy per unit volume, that'll depend on what happens to the viscosity of your solution. In some cases, the vortex mixing and a magnetic stir bar will be enough given the solution viscosity even after additives are added. In some cases, we'll need to manually shake solutions. We'll have to use overhead mixers as well, just to make sure that those particles are dispersed correctly. In some cases, to avoid any agglomeration between nanoparticles, we'll use a surfactant to make sure that the dispersion happens correctly, or a surface treatment such that the particles will repel each other and stay away from each other in solution so that we don't run into any clogging or strange viscosity or uniformity issues within our solutions. When to mix the polymer, this becomes sort of a very empirical process, which it took us a number of iterations with some of our projects to find that creating the nanoparticle solution and a polymer solution separately and then adding them minutes later after vortex mixing both, that's what we have in our standard operating procedure for a lot of our projects now. But most of that comes from mixing the polymer solution and the nanoparticles and then spinning and finding out that the uniformity wasn't quite there. So we needed to do 2 separate steps and then mix them 15 minutes later to find that the uniformity within the nanofibers mat that we created fit the description for our customer down the line. and then adjusting the polymer solvent ratios. In some cases, we found that we're trying to optimize how much nanoparticle we can get in there to fit the customer need, depending on what their final function is for their product. And you also need to optimize that with what actually is spinnable on the piece of equipment that you have, whether it's the Innovenso PE 550 or a needleless system that we have at our facility as well. It changes between the two. So we sort of have the expertise to jump between different types of electrospinning equipment and optimizing two different production methods via that different electrospinning processes. Understanding the stability of the solution, we have a couple of analytical and qualitative control methods that we use. A lot of that is the time and temperature, but what seems to help us is understanding the conductivity, the concentration, and the pH of the solutions. And Steve, if you can go to the next slide, I'll use one of the pictures we have there to explain. So I know I'm going to start on the bottom right, but on the bottom right, that white solution that has the 1 hour line in between, you can see visibly under that red circle that this emulsion does separate after about an hour. But the way we're able to tell that and we're able to confirm that is we'll use a conductivity probe to understand that we had one value when the solution was perfectly mixed, and then an hour later, that conductivity had completely dropped, seeing that and then that's confirmed by the emulsion being in two separate phases. So for larger solutions that we have to manually mix, we really, we'll have about an hour of runtime. But jumping up to that, the two images on the top, sometimes when working with nanoparticles, we only have 10 minutes. Once that final solution is prepped, we only have 10 minutes to pour it into our electrospinning system, whether it's the Inovenso or our needleless system, and then to spin it at the right conditions before it already drops out. We'd used about 80% of that solution on the left. So we were able to see that with that 20% left, the solids start to drop out of solution at the bottom. Let's see. In terms of what actually happens when you're spinning, we'll talk about environmental conditions in a bit, but making sure that you have your solution uniformly dispersed in terms of the nanoparticles to avoid the agglomeration becomes huge, because you'll end up clogging your system, whether it is a needleless or a needled system. And once your nanofiber production method clogs, you effectively will lose that solution. And when you're dealing with additives that could be very costly at some point, that's a huge detriment and slow down and money lost at that point. When cleaning tools, we do try and, as long as the conditions are safe, we do try and save nanoparticles when we can. But when cleaning things and we're done with our final, the final prep of the solution, we do have to take into account more safety conditions. Just because a normal polymer solution we can remove as hazardous waste, but given the concentration and potential nanoparticle solids loading, we do have to be careful in handling that. So we make sure to wear the appropriate PPE, and work inside fume hoods just to avoid any aerosolized particles that may be in the environment we're working in. And then during the actual electrospinning, there's a potential to run into a number of different issues that we've only figured out via empirically trying things out. The first is localization of electric field. Again, everything comes down to making sure that solution is uniformly dispersed in terms of the nanoparticles. If on a nozzle system, let's say like the Innovenso PE 550, if you don't have a uniform solution being pumped through that, and one of your nozzle heads is receiving more nanoparticles and polymer solution via another or more than another nozzle, you'll start to see discrepancies between the electrospinning, and your electric field won't be dispersed correctly along the entirety of that rod in the Innovenso PE 550. So you'll have a non-uniform mat being created. And in some cases, you might not even have nanofibers forming. Changes in the Taylor cone formation. In a lot of cases, sometimes we'll add salts to our polymer solutions to help the conductivity. Now, although that'll help the conductivity, you do ultimately change the spinning parameters. And we've seen that with, I use salts as the preliminary example, but the same thing happens with nanoparticles or metal organic frameworks. You end up changing your spinning parameters and the way the Taylor cones are created. you might need a different voltage applied to make sure that the Taylor cones stay stable. Otherwise, you might not have the long, strong nanofibers required for the mechanical purposes you need in a final product. And then finally, the production yield changes and the solvent partial pressures. We added these two pictures because we had done a number of iterations where we call them bundles forming on our on the final nanofiber map we were creating, because the additives were actually changing how the polymer solution interacted with the environmental conditions inside the electrospinning chamber. We found that we would have to adjust the humidity and temperature just because the nanoparticles we added were changing the overall solution in a way that it either absorbed more water out of the air or was more easily impacted by the temperature inside the electrospinning chamber.
Yeah, I think it's something important to note with that, right, we could have, excuse me, we could have a process that's really dialed in and well established for a given polymer, but really have to rework all the way from solution preparation and suspension preparation through processing conditions to really get a matching set of fiber diameters and fiber densities when we're making these kinds of composites. And then all of that goes into other final product considerations that you're thinking about once you have a material that's working and working well. In particular, the safety of the product. Now that you've potentially added different nanoparticulate additives to the nanofibers, what happens? Can they actually shed over time? Do they present their own environmental hazard? Especially if you're talking about filtration and you're trying to capture certain hazards or mitigate certain kind of chemistries getting past the filter. You don't want to be contributing to particles then going out and shedding from your filtration system into what's supposed to be the purified air or the purified liquid stream. And then something important to consider, and I saw one of the questions come up, is as you get to higher and higher particle loadings or certain particle sizes, that can eventually start to affect your mechanical behavior, your robustness of the fiber, and things like that. So understanding what your limitations are with a particular additive or composite and what kind of tolerances you have for any changes in physical performance of the overall nanofiber mat are really important. And then there's additional disposal and environmental impact considerations on top of just thinking about the filter media or the polymer filter media being disposed of. You now have certain nanofibers or nanoparticles that are embedded in there. And some of them that you might work with can degrade in the environment, or they're effectively minerals on their own. So they don't have acute hazards, but others are things that you'd have to consider in whatever the disposal is. And all of that kind of adds up into different cost of goods sold, whether that's regulatory around QC that you might have to do on a composite or understanding of the disposal criteria. On top of the fact that if you're making, let's say, mask filter media, you might be looking for products where you're aiming for single grams per square meter of polymer in the filtration media and trying to work at things that are sort of dollars per square meter price range. But even if you're adding a 1,000th weight percent of an additive that could be a single milligram, if you're talking about dollars per milligram of your additive, then all of a sudden your raw materials cost might be above the final product cost that you're looking for. So I think when you're looking at these, you really do need to be thinking about the added value and specific performance boosts you might be getting from the different additives to the use case. But all that being said, those are all sorts of cautions in terms of things that we think about when we're doing different composite electrospun nanofibers. But we've produced a number of these composites, both at a lab scale and full commercial scale, and using additives including carbon nanotubes, silver nanowires, different ceramic nanoparticles, metal organic frameworks, as well as some other chemical additives. So we've had projects where we've done fragrances or preservatives, even pharmaceutical ingredients like different steroids or antibiotics into nanofiber media and other polymer composites as well. And we've done it off of at least a couple dozen different polymer systems. So it is very feasible to do this. Those are just some kind of teaching warnings that we want to talk through in if you're picking up a new project or composites project, some things to think about, especially with electrospun media. And I think that all of these kinds of different composite options really can bring unique performance and function and value. And that's where we look to our clients where they're trying to find those and make sure that we're providing solutions that really make sense for them. And with that, we're happy to take any questions you might have. This is just a few of our team members, but really through Materic, we provide a full suite of expertise, not just Mike and myself. And we're always happy to talk about our experiences in electrospinning as long as we're not giving away anything proprietary for a client. And we ask you to kind of challenge us with your hardest problems because we're excited to try to meet them and figure out solutions for them. Our emails are at the beginning of the presentation. You can also email us at info@matericgroup.com, but we're also happy to take questions live from the audience.
Perfect.
So thank you very much, Dr. Stefan and Mr. Mike. And really, it was a great presentation, and really thank you for your efforts and joining this webinar. So we have Dr. Stefan and Mike, we have quite questions for you waiting. So my colleague Omar can read those questions for you, and if you can answer them, we would be really happy.
Right. So the first question that I see on the chat is, what's the deposition method used for the MOFs, and what's the impact of the MOFs on fiber morphology and adhesion?
Yeah, great question. So we were primarily working with some modified UIO 66 MOFs. And so there's a number of different MOFs that are available. And one of the things that's unique to them is you can tailor their chemistry. So we were working with some amine functionalized kind of exterior functionalization of the MOFs. And that helped with the integration into the particular polymers we were working with. In terms of mixing, basically we did what Mike had shown in the presentation, where we mixed the MOFs in a solvent system using some aggressive mixing energy, so Horn sonifiers, and then would go in, mix that in our prepared polymer solution to work that way. And luckily, MOFs are pretty small and pretty buoyant, so they seemed to hold well in terms of suspending for a long time. And we could, there are a number of modifications, but we could run it through kind of traditional electrospinning units once we had the solution prepped appropriately.
And just on the production side as well, with the MOFs, depending on the solvation level, and it totally changes your spinning conditions. If you have something with a lower solvation level, you'll actually end up absorbing more solvent from the polymer side of the solution, and you might have less conductivity in your solution, and your nanofiber throughput will be a little bit less. So you might have to change your substrate speed conditions so you can get to the same thickness that you would as if there was no MOF added in there as well. So it becomes a little optimization after adding the MOFs there.
Yep. And then in terms of fiber morphology, I think the MOF particles were small enough that it wasn't interfering too much with the fiber morphology once we had the formulation locked in. Like, it ended up changing what solvent ratios we needed and other things, but we were still able to get approximate fiber diameters where the pure electrospun polymer would also target.
Okay, thanks. So let's go on to the other question, which is, what is the maximum loading of nanoparticles you managed to add to a successful electrospinning system, and at a medium or large scale, like for example, in weight percentage?
Yeah, so probably the highest weight percentage we've been able to get is out of some of our ceramic particle composites, and we've gotten up to about 50% weight loading, which is actually quite high. I think the weight loading can be deceptive because sometimes the particle can actually be quite dense in terms of its mass to volume ratio compared to the polymer. I think the really critical limitation ends up being the effective volume fraction of the particulate into the nanofibers. So if you end up at above 20 to 30% particulate by volume interior of your nanofiber, then the particles are effectively touching each other along the nanofiber itself. And you'll start to see mechanical degradation of the fiber. So that's probably the hard limit that I would say is about 20% by volume before you start to see the fibers really start to degrade and shed. So that's kind of the highest weight percentage, but that's quite high, especially if you're talking about something that's going to be a catalyst or this kind of active chemical ingredient. You can get to pretty high loadings.
Thank you.
Okay, thank you. So another question is, what is the solvent for the solution in the nanoparticles? Let's see if we can make that clear.
That one is a DMF, if we're okay.
Yeah. So for those particular images we showed, it's DMF. There's other ones that are proprietary to specific client projects, but usually we're working with some of the native solvents we would work with in the pure polymer system. And then we are doing some fraction of that solvent mixed with the particles. That way we can just directly mix it back into the polymer solution and just target our final solution ratios.
Okay.
So it doesn't have to be DMF. We can work with all sorts of other solvents too.
Right. So is the probe sonicator more effective than the vortex mixing, and were you able to characterize the aggregation of nanoparticles in your solution?
So, I was gonna say, you want me to?
Yeah, why don't you take a first stab? Yeah.
Sure. So the sonication, I think, is, if we're looking at which is more effective, the sonication is definitely the more effective in removing the agglomerates for nanoparticles. The vortex mixing is just a secondary method to make sure that they're well dispersed. And once we mix two solutions, the strictly polymer solution and then the nanoparticle polymer solution, when we mix those together, we'll then vortex mix it to get that final dispersion well throughout the entire solution. But the majority of the de-agglomeration comes from the horn sonification.
Yeah, and when you think about it from a first principles standpoint, all the different mixing options that we use are about kind of energy per unit volume of solution we can add in. The more energy we can get into whatever that volume of liquid is, the more likely we are going to be to disperse particles. And with nanoparticles, the smaller they get, the more likely they are to agglomerate with each other. So sometimes we have to use very high energies like a probe sonicator to really do that. But those kinds of energies, maybe the nanoparticle is robust to that, but the polymer might get cleaved and you'll get changes in molecular weight. And so we really try to do that on the nanoparticles in the solvent without having polymer in there at that stage so we don't hurt it. Yeah, hopefully that answers that question.
Thank you so much.
Thank you.
Nicholas Torasso says, thank you, Stephen.
A lot of thankful messages there.
Yeah.
Really, we appreciate for
a lot of thank yous.
this, presentations. Right. So we have one last question.
Let's see.
Let's see.
Hello.
Hello.
Yes, we can hear you. You can ask your question to Dr. Stefan and of course the mic. Okay.
Thank you, Stefan and Mike. Great presentation. So my name is Singham. I'm a PhD student at the University of Guelph, Canada. So I have a question regarding the polymer solutions. So you guys mentioned that you guys use DMF as an example as a solvent. I was wondering, most of the time we face problem of this high volatile or high pressure solvent being vaporized very fast, and we ended up having the solvent like dried up first and having the solutions like solidified very fast? How do you guys maintain the polymer solutions stability for a little longer time so that we can spin it like for longer?
Yeah, I mean, that's something we work on all the time with different polymers and different solvent systems. A lot of the solvent systems we use, we're using multiple solvents. So a binary solvent system has been useful to sometimes have low boilers, but also high boilers in the mixture to try to get some control over that and prevent too rapid a drying. Then other times, depending on the solution, especially like if you're doing a probe sonicator and you're working with a very volatile solvent, it's hard to have the probe in there and not have some solvent evaporate. So sometimes it's just looking for mass loss and kind of compensating for that. So I think that's a challenge across the industry for all sorts of folks, depending on which solvents you're working with. So it's either tracking mass loss or working with the right complementary solvents to try to give you some more workable time. And I'd say especially if we see that kind of issue especially important and often have to work with reformulations when we're moving from a lab scale system to a roll-to-roll type system. When you have a potential clog in a lab scale system, sometimes you can just knock it off or use the tweezers to get rid of it. But when you have dozens of nozzles all trying to work simultaneously, if you have any of those issues, they get exacerbated. And so I think a lot of that, as you move to industrial scales, you often want to go with higher and higher boiling point solvents a little bit. You tend to trend towards things that are going to stay as a liquid for longer so that you prevent clogging or too rapid a volatilization.
So
thank you very much. One last question, sorry. I was wondering, you guys are working on some filter for mass or like respirator filter kind of. So like you guys mentioned that you guys use some kind of nanoparticles. I also saw you guys have put the antimicrobial kind of stuffs. So are you guys working on some kind of antimicrobial mass or filter for respirators or something like that?
So we're really a custom development shop. So we have clients that work in filtration media. We have clients that work in biomedical applications and wound healing, and other folks that are in textiles or like industrial liquid filtration. So we don't have one specific product that's a mask filter or an air filter. We did manufacture in the early days of the pandemic just to supply locally, but we don't have a specific filtration product that we make and sell. We really do custom work for individual clients. So none of the filtration, none of the mask materials that we were making on kind of an emergency basis, we didn't put any additives into that, although we got some custom requests for people who wanted to do develop their own specialty products to try things like silver. But we hadn't finished process validation and other things that we weren't going to put that out on people's faces at that stage of development.
Thank you very much. I think Dr. Kevin has mentioned that they're working on antiviral filters. Okay, so a great presentation. Thank you very much for the clarification. Yeah, I would like to come back to Dr. Kevin if he's available.
Yes, I'm available. Thank you for the question.
Yeah,
sorry for jumping.
Yeah, no worries. Actually, I was wondering, like a lot of people ask, like air filters, this antimicrobial silver, like I mean, these metal nanoparticle stuffs. So a lot of people ask, like if they are incorporated in the fibers, like while breathing or something like that, will it be coming into our like systems or something like that. This kind of like scary questions they are asking. So how are you going to validate the products you're like developing, like making them like it's safe for use? So how to answer to these questions? I was wondering this question for quite some time.
Yes, is that question for me?
Yeah, sure.
Okay. That's a great question. Thank you for asking that question. Well, I think we have done like some study on the antiviral properties of nanofibers, and we did send some like our own developed sample to a third lab testing, and they have a really positive result. And a lot of time people using like a metal oxide nanoparticle to achieve this kind of property, but most of those metal oxide was like registered as a pesticide in EPA. So if you want to develop like a face mask using those like particles, it's really hard to get the FDA approval. So, but in our research, we use a really bioactive component, which registered in the FDA as a food. So in that sense, like this kind of the product we developed is a really bio-friendly product, and it doesn't function like those metal oxide. So did I address your questions?
Yeah, thank you very much. Yeah, like I have seen people are working on metal nanoparticles using as antimicrobial antimicrobial functional materials on masks or filters. So that's when people started asking like, because it's not always possible that it will incorporate inside the fiber, right? Some of them may detach from the fiber and come into our breathing systems or like our body systems. So
yeah, and I think QC for that is very, very challenging, right? To actually try to characterize how many nanoparticles might be shedding. So I think it's an open question in the community, and that's especially for something that some.
Dr. Stephen, are you there? I believe there
seems to be an issue.
Yeah, there seems to be an issue.
Dr. Stephen, we lost you. Dr. Stephen, I think we've lost your trace. Okay. Are you still there? Let's see if we can get something out. We'll take a look at that while it happens. While we wait for Dr. Stephen, maybe we can try to look at the other questions and see if we can help answer them. So let's see the next question.
I believe they will join in a second. Just a moment.
Right. So both of these next two questions are actually addressed to
Dr.
Stephen
yes.
and Dr. Mike. So we can wait for them while we fix this issue. Right. So actually, let's see if we can answer some of these questions on our own. Let's see. So Mr. Raghunath Tarwat actually asked, can you please clarify if nanofibers used as air filtration in HVAC system or HEPA filter alone or as coating for original filter? May I ask this question in the previous lecture? Okay. So thank you for your question, Mr. Raghunath. Actually, it depends on what type of product you're. There's no strict definition. You can use nanofiber membrane media for HEPA filters or HVAC. Although there's different quality tests assured from, like HEPA would be a high quality HVAC filter, so it doesn't necessarily need to be just a coating or a single layer, unless you have a specialized design, which in that case you can achieve something like that, but in experimental stages for now. So I hope that answers your question for the first part. So the next question, I believe Dr. Stephen is best suited to answer that. Let's see if we can get him up and running.
Yep, sorry about that. Zoom seems to have reset, so I'm on my cell phone right now. Can you still hear me?
Yeah, we can hear you, but we can't see you.
Yep, I'm going to have to find a set up for the cell phone, so I'm happy to kind of just talk live.
No problem. So
Okay.
we can go to the question sheet and see if we can get these questions answered. Let's bring
see
up,
the questions, please. We have one more
Mhm.
question from Ms. Ragda. Can you please go
So
a little
let's
bit
go
up?
a little more. Yeah, see the question. Right. So what is the application of carbon nanotube as additives in nanofiber, and what is its specification for this purpose?
Okay, so I think some of that's proprietary to our clients, so we've got to protect their specific applications, but I can talk broadly. Within carbon nanotubes, there's different capabilities for electrical and thermal conductivity that carbon nanotubes are known for. And so, and the other thing, because of their very, very large aspect ratio, you can often work with small concentrations of them to get reasonable to large changes in properties of a material. So it's kind of under those broad categories, but unfortunately I can't get into the details because it's related to specific clients.
Right, it's understandable. So let's go to, I believe, the last question for this presentation. Yeah. So Mr. Federico Trupp asks a specific question. If we can open the file, let's see here. Right. So could we go to a little bit down to the sheet, please? Okay. So yeah. So Mr. Federico Trupp, thank you for joining. So he asks for the less stable solutions. Don't the nanoparticles like agglomerate or decantate in the syringe or reservoir during this process? Thank you for the great presentation.
Yeah, so, and like I said, especially for more volatile solutions, that can be an issue. And so for some of those solutions, we only have a matter of 10 or 15 minutes to work with it if we're doing kind of a small system. I think that there are options when it gets to the continuous feed or continuous pumped feeds into the different systems that they can then work with that because you can do different agitation to kind of keep things in suspension up until it gets to the actual spinner head. So in some ways, the commercial scale instruments are a little bit easier to work with because you can have better control over pumps and dwell times and things like that. But it's definitely an issue. And all of that comes into one of the earlier slides we said in terms of trying to design your formulations and your mixing steps from the beginning to get as much time in suspension as you can. And sometimes we have to study that, like we'll put the suspensions in DLS instruments to see how quickly they're agglomerating and try to characterize that, or just use some visual cues that things have dropped off to figure out how much time we have to actually work with that suspension.
Right. Okay. So
thank you so much for the answer.
Yeah, for the
if you have any further questions for Dr. Stephen, you can ask him
Mike,
via email.
Yeah, they had a very good presentation and really good answers. We thank both Metrogenics and
Materik.